Hello everyone, my name's Ryan Malder, and here I'm going to be talking about the Maxwell-Boltzmann distribution function. It's a probability distribution, and I'm going to be kind of looking into an example of a one-dimensional particle, how this probability distribution function works for one particle in a three-dimensional system, which we'll consider that three-dimensional system as a sphere, and we have our particle centered in the center of the sphere. And it's also called the Maxwell-Boltzmann. Clark Maxwell was the man who worked with this distribution function, and Boltzmann, that's means for classical distribution function, and Boltzmann was the one that pretty much theorized it. But anyways, this is also very good with if we apply this one-dimensional particle to many particles in, say, a given system, say in this sphere we have here, then this will be very useful for molecular dynamics, because that is also like GROMACS. That's also a three-dimensional system modeling many particles in a system, usually at equilibrium, because we want things to be at equilibrium. And this Maxwell-Boltzmann distribution function we'll be able to look at how does a one particle in a three-dimensional system, which behaves at equilibrium. And kind of look at what is the number of classical momentums that this one-dimensional particle in our sphere can have. We can also look at this, use the same distribution function and look at it into what is the number of quantum momentum states. But here we're looking at classical, and we're going to look at what is the number of classical momentum states in a given system at equilibrium. So yeah, I might turn this way. And so, let's start off. What is the distribution function we need? And we're going to need this equation here, which gives us we're going to look at the probability density versus the velocity of our one-dimensional particle in our sphere here. So this is a probability density, and this is equal to this equation here, to this distribution function, which we're going to have to integrate that's pretty much all. We'll always have to integrate. So this is our distribution function. This is our classical Boltzmann distribution function. We're going to determine momentum is also made up of velocity, because we call momentum is mass times velocity, or the change in velocity. It's given by this equation here. And now we want to say that our particle here is in our system is at equilibrium. We want to integrate over all the average square velocities, which is the RMS, the root mean squared of velocity. So that'll tell us that'll average out. This distribution function will therefore average out all the possible momentums or velocities our one particle in a three-dimensional sphere here will have. And we're going to, so using our distribution function, we're going to set our integration values from 0 to infinity. And our distribution is equal to the probability density is equal to this v squared average. The line up here means average. It's taking the average of the velocity squared. Oh, and also beta is equal to 1 over kt, which k is Boltzmann's constant, t is temperature. So integration from 0 to infinity. And we plug in, here we're plugging in v squared. Just put v squared because we're wanting to know was the RMS. So this will be v squared squared. And we take e to the minus beta m v squared over 2 dv. And this exponential function right here, this is the classical probability. If we were going to look at the quantum, this will have like another added term in the exponential. But since we're talking classical, it's just mostly multiplication and division up here. And little m here is also the mass of the particle. Okay, so now we have this distribution function. We need to, and here we have to integrate over all of the average velocity squared, the RMS. And so we have to solve this integration. But this integration is also very tough, as you can see, because we got this v to the fourth and then this exponential term multiplied. Makes it a little bit tricky to work with, but there's an integration trick to get around this integration. So to recall this integration system, in which if we take the integration of infinity minus infinity, e to the minus ax squared, and then times x to 2 times x2 power of 2n dx, that this is equal to this is equal to 2 times the integration from 0 to infinity, e to the minus ax squared, x to the 2n dx. Basically, all of this is therefore can also be reduced down to it's 1 times 3 times 5 times dot 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 times 2n to the minus 1 to this kind of series, which over 2n an times pi to the over a to the 1/2 power. And the reason why we have this pi over a to the square root of pi over a, this comes from integrating a Gaussian. When you integrate a Gaussian, it gives you the square root of pi, and a is just a constant, so it's whatever the constant up here in your exponential, which is your Gaussian. That's what a is. It's just constant. Could be 1. But whenever you integrate a Gaussian, you get the square root of pi, and that's what this is here. So we can therefore apply this integration technique to help us solve this integral up here. So we'll have our constant out in front, 4 pi beta over m over 2 pi. And so our integration, using our integration here, this is just equal to here. So yeah. So, anyways, where was I? Yep. So we take, so what is our n here? Our n is, if we look over here at this equation here, x to the 2n, and back up here, this v squared squared, so that means our n is 2. So if we go over here, there are 2n minus 1, we just plug in 2 into there. That'll be 2 times 2 is 4, minus 1 is 3, so it'll just be going up to 1 times 3. And then that means our 2 to the 2 squared, that'll be 4. And this will be 1 over our constant, which our constant will be our beta times m over 2. That'll be squared. And hold on, my battery is low. Alright, so now we got some full battery. So now we charge computers. Now we got our constant here raised to the n, which is squared from right here. And then that'll be multiplied by our integration of the Gaussian, or square root of pi. So that'll just be the square root of pi over a, which again will be beta over m over 2. And that's pretty much what our distribution function up here comes out to be. Just this big long line of constants being multiplied together. And so we can go ahead and start kind of canceling some terms and combining our constants here together, which the 4 here will cancel, as well as the square root of pi will also cancel. And I did forget a little something. This term right here, that's supposed to be 3/2. Alright. It's supposed to be raised to 3/2. Got about that 3/2 power. That's what I was forgetting. So whenever we combine 3/2 to 2, beta over m to the 3/2 power, and then 2 raised to the 3/2, that would be equal to 2 square root of 2. And we multiply by 3. And then we have beta over m squared all over 4. And we have the square root of 2 over beta m. So and then we can cancel out that square root with this square root up here. And we will, and then this should also be, this should be flipped over. This should be 4 over beta m squared, because here with our division here, beta over m squared will stay on the bottom. In the denominator, 2 squared will be moved to the top, to the denominator position. So when we write this, 3 times 4 is 12, which will be 12 over 2. And then our beta m's here Whenever we combine them all together, we're just going to get a 1 over beta m. Beta m, and this is again equal to the average velocity squared. And if we were to rewrite beta in terms of k and t, we will get 6 kt all over m, the mass. So, and this is the RMS for velocity of the particle. This will be this here will be the average velocity squared, 6 kt over m. And this is the RMS velocity of one of our particle in a three-dimensional sphere, calculating what is the number of classical momentum states in a given system at equilibrium. This will give us essentially the RMS velocity, averaging all those velocities of all those different states, and they're all going to, and so velocity squared is related to the temperature. If you were to increase the temperature, then the RMS velocity will increase. Likewise, if you decrease temperature, the RMS velocity will decrease. So this is very important because we can link this RMS velocity to energy. We can link this RMS velocity with respect to energy. And if you recall, what is kinetic energy? Kinetic energy is 1/2 mv squared. And this velocity squared here, this is our RMS velocity. So I'm going to write Ke as E. This is also related to energy. Kinetic energy, they're all energy. So if we were to plug in our RMS velocity into kinetic energy, then we'll have 1/2 m 1/2 m times 6 kt over m. We'll see that the m's will cancel. And so 6 over 2 will be 3 kt, and this will be how much energy our one-dimensional particle in a sphere has at equilibrium. How much energy that particle has at equilibrium. As you can see, if I were to increase temperature, the energy for that one particle in our three-dimensional sphere will increase. And turns out this 3 here can be written using the Greek letter nu, this curly v. This is related to the degrees of freedom. To the degrees of freedom, particle has in the system. The particle has it in the system. All right. So we can write this into a more general form where the energy of a given particle in some system is related to the number of degrees of freedom the particle has times the Boltzmann's constant times the temperature. And we can therefore, this is how we can describe this is a theory called the kinetic theory of molecules. Kinetic theory of molecules. Oh, I forgot theory. This is the kinetic theory of molecules from here, which you may have seen it as written as 1/2 m v squared, the kinetic energy, the RMS velocity is equal to 3/2 times kT, which are 3 here. It tells us there's 3 degrees of freedom. 3 tells us 3 degrees of freedom. So this kind of links up kinetic energy and how much this will be in form of heat energy, or how much quantized energy, well, how much classical energy is a particle has in a three-dimensional system. And we can therefore solve for this RMS velocity to check, make sure it matches with So this is the kinetic theory of molecules. Very important whenever you're working with any kind of molecular dynamic simulation. It's all some kind of classical approximation. And this, again, is derived from the Maxwell-Boltzmann distribution function right here. And that's all we have. And that's it.